All right, this is what we're looking at next week, this week. Review today, and I'll kind of do that in reverse order. So I'll go over the homework you just did, not all of it, but a couple of them. That'll be very similar to what you'll get on Wednesday, right? And then we'll work our way backwards. So we're in chapter 4. So when I work the homeworks, it'll be like a review of chapter 4, right? And usually that is the least amount of review we have to do because it's current, like you're doing that homework. What you've kind of forgotten is like chapter 1 and chapter 2. So
the normal length for that class is like from 8 to 9:50.
Yeah. No, I mean, it'll be 8 to 9:50. But I'm not that interested in time being a factor. I'd rather know what you know. So if 9:50 comes and you want to keep working on it, I'm fine with that. I don't think that will be the case. There's not that many problems and they're not that long. So like if you're still grinding on it at 9:50, there's probably other problems going on, but I don't want time to be a factor. Like that's not what I want to test. I want to test your knowledge. So yeah, we'll go with that. And I know there's at least one person that's going to do it online at the same time. So they can't be here because of kind of childcare issues. So they'll be doing it online, but at the exact same time that you're doing it, and I'll email it to them. They'll do it while you're doing it, and then they'll email it back. So that's what's going on. And that option's for anyone. It's not the best option because you can't ask questions like as easily, right? They might email me a question and I'll try and monitor that, but it's way better if you're here in person and you can just say, hey, I don't understand this problem. Like, what am I supposed to do, right? Because that's not what I'm testing you on either. I don't want to test you on your ability to figure out what I want, right? I want you to like know what you're supposed to do and then do it. So straightforward as possible. All right, and we'll do that Wednesday. And then we'll just keep going. So I'll probably produce a lecture here that might push us into chapter 5. Then you have a little more chapter 4 homework here. So, and then we do the mobile lab next week. So if folks can come, it's way better, obviously, in person. I don't know how to do it not in person. So we're going to design and build equilibrium systems because that's what we just did, equilibrium. So they're hanging in the back of the room. Those are mobiles. And anyone can build it trial and error, but we don't want to do that. We want to calculate it all out, mark it all out, drill it once, assemble it laid flat on the table, and then hold it up and see if you calculated things correctly. So it's usually pretty fun, but we'll do that next week. All right, so let's go over. So 16, several folks had problems with 16. I went through the homework and the quiz. So there was problems on the quiz and there was problems on this one, which I'm not sure exactly why, but I want to go through it and make sure, because this is very similar to something you will get on Wednesday. This one said, find the reactions at A and B. Okay. So when you get a problem like this, especially Wednesday, it's good to like categorize it in your head, right? Hey, if it's saying find the reactions, then you are working with equilibrium. And that's those 3 equations, right? If it says find the resultant, and I'm sorry, they both start with R, they do. But if it says find the resultant, you're not working with equilibrium. So the big problem that students have on Wednesday is it'll say find the resultant, and then everyone goes for the reactions. That's not what we want. If it says find the resultant, you just want to take these 2 forces, concentrate them, and then find the single force that could replace them. So that was like chapter 3. So that's the big confusion. Chapter 4 is find the reactions. And reactions are, if I get rid of the support and put in the reactions, AY, AX, and BY, right? I get rid of those supports. That's the free body diagram. That's chapter 4. These are reactions. There's 3 of them. Okay. These are external forces And if I combine the external forces into one force, that would be a resultant. Two different creatures. We don't do resultants when we're doing reactions because everything's equal to zero. There is no resultant. So if that's still not clear, try to get that clear before Wednesday, whatever it takes. Like, we got to figure that out. All right, so what do we do on this problem if we want to find the reactions, these three? What do we have to do with these distributions? We don't do any moving, not when we're doing reactions. What do we do with distributions in general? Do we leave them like that? Come on. What do we do with distributions?
So on the left side of the 16.
As soon as I say it, you're going to know what I'm asking for, but no left side, no right side. What do we do with the distribution? If you're given a triangle, what do you do with it? You leave it that way? Like if I'm going to sum the moments, how would I do that? Yeah, you got to concentrate the distributions. You got to get rid of them. Turn them into a single force. That's the first step. Anytime you see a distribution like this, or any other distribution, all of those, step one is get rid of them, concentrate them. Okay. How do I concentrate a distribution? How do I get rid of this rectangle? Yeah, calculate its area. So you can do this a couple different ways. You can use this 2 foot, or you can use this 1 foot. And I think that's where people got confused, because this is 2 foot right there. So I can use this rectangle and concentrate it. That's how I would do it. How tall is that rectangle? It makes a total difference. Like the way you concentrate it is the area. You got to know how tall it is. Area, right? Length times height for a rectangle. What if it's a triangle? 1/2 base times height, right? What if it's some parabolic curve? That'd be rude if I did that, because we haven't done one yet. But what if it was? How are you going to concentrate some crazy parabolic curve? Front cover of the book has the area of some crazy curve right there. So yeah, we have to know the area. That you got to know the area, then you got to know the height. How tall is this? If this is 2, if this is 1, and that is 2 up here, how big is this? Yeah, it's a graph. So like this is 2 all the way to the top. And this is 1 all the way to its top. So that's got to be 1 and that's got to be 1. So it's easy to, when you have multiple distributions, it's easy to screw that up.
How would you know that? Was there like cases where the distance is 3 or 4?
Well, the only way you're going to know it, Ben, is to really slow down and try to figure it out. Like, what's this one? Two distributions, right? How tall is the rectangular distribution? Don't overthink it. Oh, right there. Sorry, maybe I just didn't give you a good enough arrow. How tall is the rectangle? 6. So how tall is the triangle from here to here? 6. It's a graph. If I said from here to here is 6, How tall is this? 6. So then if I said from here to here is 12, how tall is this? 12. So then how tall is that? Yeah, same thing. Same exact thing, right? We're 6 here, we're 12 to the top, we're 6 there. So yeah, you just gotta like draw extra pictures, right? Or whatever it takes. All right, so this one is 1 and this one is 1. So I would concentrate them separately. You can break distributions up, concentrate them separately. So how big is this rectangle? Yeah, 1 times 16. And where do I put it? Halfway. So this is 8 over 8 feet, and it is 16 kips. Because I just did this piece, right? This purple rectangle. Now I'll do the bottom one. I'll even give you different hash marks. Yeah, so it's 1 times this distance, 26, and then where does it get applied? At 13, yep. So I'm doing it all on this thing. If it was me in a homework, I'd draw a new beam and just have these two, but for the sake of time, I'm not redrawing stuff. So I have now a force 16 kips and a force 26 kips, and my 2 distributions are gone, right? So if I did redraw the beam, and I'm gonna, because I just want it super clear. It looks like this. 16K and 26K. This is 8 feet over, and this is 13 feet over, right? And then I have BY. So this is the new free body diagram. AY, AX, right? The pin's gone, the roller's gone, the distributions are gone. This is a good, clean free body diagram. That is also 13. So this distribution is probably the weight of the beam. When you see a uniform distribution throughout the beam, that's probably the weight of the beam. And then this is some extra load. Cool. So now this problem asks for the reactions. That's why these 3 are in here. And then that's the goal. If you're asked for what are the reactions, we want to know what these loads are on the supports. Pick out the easy one first. Which one's the easy one? Would what be 16? Help me out there. When I say easy one, I'm talking about the 3 equations. And they're all got to be equal to 0, right? Because that's our equilibrium state. Everything's equal to 0. Moments, there's no rotations. Forces in the X, forces in the Y, all have to equal 0. So the easy one is there a force in a direction all by itself and nothing else? Yeah, X is the only force in the X direction. So if I was to write that equation, it looks like I wrote it minus AX equals 0. So I just summed all the forces in the X. There's only one. It's got to be equal to 0. Done. AX equals 0. That's one of the 3 reactions. So that's one of your solutions right there, just by picking that thing out. How many forces are in the Y? Correct. How many unknown in the Y? 2. So if I write this equation, I'm going to end up with 2 unknown. And I will not be able to solve it. It might help me in the end. Like if you don't know what to do on find the reactions, just do the equations. Do all 3. And I can say that 100 times, but come Wednesday, somebody will get this problem and they will not do the 3 equations. Like, why don't you just do the 3 equations? Like, if you don't know what to do, just apply these equations. So summing forces in the Y, tell me what all the forces are in the Y direction. Plus or minus? Minus, because it's pointing down. Yep. What else? Minus 26. Don't forget your unknowns. Whoops. BY. And we set that equal to 0. So that's great. That's points. When I look at it on Wednesday, I'm like, oh, they know how to do that. They know how to sum forces in the Y. That's perfect. We can't do anything with it. There's 2 unknowns. 2 unknown, 1 equation, no bueno. So that leaves this. How do we sum a moment to help ourselves?
Force times distance.
Yep. What do we have to do to sum a moment? What decision do we have to make? Yeah, we have to choose a spot to sum the moment. Got to pick a spot. We want to pick a spot that eliminates one of these unknowns. In other words, if I pick out here somewhere, AY creates a moment and BY creates a moment, I'm going to end up with 2 unknowns again. I did not help myself. So you want to pick a spot that eliminates one of the unknowns. And if our moment equation is force times distance, something does not create moment when distance equals 0. So that means I need to pick either A, because then these 2 drop out, or B, then this one drops out. One of the unknowns drops out. Okay? Most of us pick A because we're right-handed or we read left to right. I don't know why we do it, but we do it. Right? And I don't care. This is going to be up to you on Wednesday. Pick whatever spot you want. Right? Just pick a good spot, a smart spot. So if we did moments at A, then now I just am doing force times distance, collecting them all at A, just like we've done a lot of. So what are the moments at A? 16 times 8. So the way I do moments is I just do force times distance and then I think about rotation, right? And I leave myself a little space for the sign. So this is going which way around point A? Clockwise, which is negative. Excellent. And so come up with a system. Like the way I do it is I start here and then I go here and I go here and then I come back around to here. So I just work around the system, right? To make sure I don't miss any. So then I would go 26 times what? Oops. I don't know where that came from. Plus or minus? Minus, rotating clockwise still. Then what? BY times 26. And I drew it pointing up, right? That was my assumption. When you put reactions in, you are assuming a direction of rotation. I assume this going up, right? So that means I'm assuming that this rotates counterclockwise around A, which is positive. That's super important. And then what about AY? About point A, does it create moment? Nope. What about AX? Nope, they both go right through the point. So this is a great spot to choose because 2 forces drop out. This is a good spot to choose, but only 1 force drops out, right? Actually, AX drops out too. So, all right, set it equal to 0, solve for BY. So I'm going to leave the BY statement right there because it's positive. Okay, let me work with you on that. So if I'm leaving this algebraically, if I'm leaving this right here, Ben, right, I'm not moving it to the other side because it would then go negative. Right, so that makes it what? No, when you move it to the other side, it changes sign. becomes positive.
What if you calculate all the momentum together, you get a positive with that?
Negative plus a negative is negative.
Oh.
Yeah. And then you move it to the other side, it becomes positive. So I get a positive number divided by 26, which is a positive number. I get 17.923. So I'll do that again just to make sure I didn't make any mistakes.
That's 292.
26 divide, yeah, 17.92. It comes out positive, which means BY is going in the correct direction. If you ever get a negative number here and you're very careful with your signs, that means you assumed the wrong direction. That's all that negative means. So that's a very hard concept to kind of grasp, but since this came out positive, that means BY does point up. Okay. If you don't give me this arrow, then I'm going to assume your sign is the way you think it's going. So if you give me a positive number, I'm going to assume you're thinking it's going up. You give me a negative number, I'm going to assume it's going down for the Y. All right, then you can get AY by plugging this number back into this equation. That's probably the easiest way to do it. You could also do another moment. You could do a moment here to get AY. That would be fine. Completely up to you, however you want to do it. I would stick BY in here and get AY. So if I did that, I'm going to leave AY there. BY is going to go negative minus BY, right? Because I move it to the other side. And then these two go positive, and I'm just going to turn that into a number 16, and 26 is 42. Okay. So I just combined these two, moved them over, it became positive 42, and then BY moved over, it became negative. So then AY is 42 minus 17.923. And that is 24.0708. Hold on, what? I'm ready for you.
Oh, I did times 17.
Oh yeah, don't do that.
Whoops.
So think about forces in the Y, they got to balance out, right? I mean, we want forces in the Y equal to 0. So how much down do we have? 42. So how much up do we have to have? 42. So if this one's 17.923, then this one has to make that 42. So that's the 24. Yeah, it gets a little more complicated. Just turn your angled forces into X and Y and go after it. Then it looks a lot like this. An absolutely lot like this. It's longer, more time consuming, more opportunity for mistakes, right? Because you're turning forces into their components. But just go slow, be careful. That help? Hopefully that helps. I want to go over the quiz. It was very similar to that. I think you had to find these reactions. Let me make sure. Yeah, it said beam supported non-uniform distribution shown. Calculate the reactions at each support. Neglect the weight of the beam. So It says calculate the reactions. That means I need to put in the reactions for the supports. So a pin, how many does a pin get? 2. 1 up, I'm sure, because there's a lot of force coming down, but I am guessing By. And then 1 in the horizontal. Do you see any horizontal forces on this system? No. So you can point it either direction and you can just say it, right? If there's no X forces externally, then there's no X forces internally. Nothing to balance out. Yeah.
So far we haven't
Oh,
gotten any export throughout our.
Yeah, we did have one, and I'm gonna work that problem. Right, we had X forces all over this thing. That was one of the homeworks. Tons of them. Yeah, good times. So I'll do that one next. I'll do that one next. It just, right, it's a lot of forces. It looks hard. It's no different.
Without the export forces, it seems so simple, but when you add.
Well, not only adding X force, but you're adding Y distance. You're adding structure to it, right? Where this kind of stuff has no Y distance stuff going on, right? So it is more complicated for sure. All right. So BX 0, BY going up. How many for a roller? 1. Which way do you think it goes? Up. Emphasizing that that's a guess. All of that's a guess. Like here, let's have a bad guess. I want to say AY goes down. I don't know why I'm saying that, but I am. I'm going to say BY goes up, AY goes down, and I'm going to let the math tell me I'm wrong. All right. What do I do with this distribution? Hopefully we know that one now. What do we do with it? Or concentrate it, right? And I always draw pictures. So there's my rectangle. I'm going to split it into 2. I mean, you can look up a trapezoid and do it. I just split it into 2 and go that route. So rectangle, how tall is my rectangle? 3. And how long? 22. So what's that? 20, 40, 66. Yeah. 66. And where's it go? 66 kip in the middle, correct? So 11 feet. Wait.
If you do the one with the 7 feet, is it also going to be in the middle as well?
Whoa. Let's just do the rectangle first. Are you happy with the rectangle? Yes. Okay, now let's go to the triangle. How tall is the triangle? 4. Yeah. So now we got, and it goes all the way to the end, right? So what's the area of a triangle? It's 1/2 the base times the height, right? So 44. Did I do that right? I just took 1/2 of 4, 2, and multiplied. Yep. And then where's it go? Geometric center. Anybody remember where that is? Yeah, from this 90, it's 1/3. So what's 1/3 of 22?
Like
7.33. feet. From B, right? Yeah. So just be careful when you concentrate it. Make sure you find your distances. And again, you know, especially for the test, I would draw a new beam just to clean things up so I don't make any mistakes. So I have BY, I have BX. I have a really bad decision on AY going down. And then I have 66K in the middle at 11 feet. And then I have 444K at 7.333 feet. That repeats. Right? And I know this is 11 feet because that was in the center. So yeah, just have to be careful with everything now. All right. How do we get AY, BY, and BX? Yeah, apply the three equations of equilibrium. And again, if you don't know where to start with summing forces in the X, and then go to summing forces in the Y, and then sum a moment. Just do them in order if you don't know where to start. We already kind of did forces in the X, right? We know that's equal to 0, and we have one of them, BX equals 0. All right, let's sum forces in the Y. What are they? Next 66, negative 44, plus BY, and minus AY. Exactly. All that's equal to 0. Don't miss any, right? Can we solve it? No. Two unknowns. So now what? Do a moment. Where do you want to do it? I like B because I know how far this one is from B, and I know how far this one is from B. If I do A, I have to do a little extra math to figure out the 44 distance, right? And I just want a simpler route. So I say, great idea, let's do B. Where do you want to start? Start in the middle. All right. I wouldn't do that. I'd start and go like in a system, but I'm good with you. 66 times 11. It's not that hard. We can figure this out, right? Plus or minus on the rotation. We need somebody to do the tiebreaker. We got minus, we got positive. We're doing it here, right? We're doing it here. So 66 is going to rotate around that way. Positive. What else? So I heard the 44 first. 7.333 and its rotation. Positive. So now we have these two. What else? Yeah, AY times 22 and its rotation. Positive. And BX goes right through the point and BY goes right through the point. So those drop out. So now we need the algebra for AY. We have to clear this statement. So this one moves over, this one moves over. Those become both negative. Yeah. So I'm going to end up with AY times 22 equals, and now I'll calculate that, 66 and the 11. No, just your store. Negative 1048.565652. Right, and those are actually kip feet because they're moments. This is feet, right? So there's the algebra where I took this, these two statements, moved them to the other side. That made them negative. And now I'm going to divide by the 22 to get what for AY? 47.66 kips. So if you've done the math right, the number is correct, right? That negative means what? Wrong direction. You made a bad choice in the beginning. AY does not go down, which we knew that. right? But that's what this is telling you. It's not telling you that the 47 is negative going down. It's telling you you made a mistake. We cannot come up with a negative sign. So that means go fix it. Okay, AY goes up and that changes the sign here. Fix that. That changes the sign here, right? When you go through, it changes everything. So this would become negative. So then when this moves over, it becomes positive. The whole statement becomes positive, positive. Okay, anytime you come up with a negative out of a moment equation, then you've done something wrong. Like there's a direction. And these are going to get complicated where you're not going to know which way it goes. Like, when we look at this one, it's like, really? Tell me which way Y goes for A. There's no way. You got down force, down force, down force, down force. Okay. I guess I could tell you that that goes up. It's got to go up. But if one of these pointed up, then I don't know what wins, right? And I don't spend a lot of time thinking about it. I just draw them in and go. Just make a guess and go. All right, excellent. Got AY, how do we get BY? Yeah, plug it back in, yep. I know that 66 and 44, that's all down force, right? So what is that, 110?
Good question.
Yeah,
So you know how we started taking the wall from B? So we assume that 66K is going counterclockwise, which is what?
no, we didn't, that's not an assumption. Right here is where we're doing our moment. If I attach a string and let go of that thing, it is definitely spinning around counterclockwise. That's positive.
On the AY going down.
It was going down originally. That's also positive, and we put it in positive.
Oh, okay.
Yeah, we just made a bad guess. But then when we realized we were wrong, I went and changed everything.
Yeah, sorry. For some reason I thought it was a negative.
Oh, no.
Mixed up with A. and
Yeah,
B.
no. So to get BY, right, I got how much coming down? 110 coming down. I need 110 going up. And I know I got 47.66, so I just kind of use basic logic on that. 110, take away the 47.66. I got to have 62.34 going up. So BY got to be equal to 62.34 K going up. It's got to be exact, not relatively close. It's got to be exactly the same. If there's 110 coming down, there's got to be 110 going up. Oh, what do you mean?
AY 47, that's close to 44. BY is close to 66.
Oh, that's coincidence. Yeah, just coincidence. Yeah, but what you can look at and say is, okay, we have a big load right here in the middle, right? So half of that load goes here, half of that load goes here. Does that make sense? And then we got a load 44 that's closer to BY than it is to AY, correct? So which one of these two are going to be bigger? BY's got to be bigger. So that's another check you can always make. If it's not too complicated, you can say, oh, there's more load on this side, BY needs to be bigger than AY. So then if you do all your math and it's not that way, then you screwed something up. Like, whoops, right? So yeah, that's always a good check. A little estimation always helps. I don't know. Usually when I do it in class, doesn't feel too bad because I'm going through it step by step and answering questions. But then when you get all by yourself on a homework problem, you're like, what? Where do I even start this thing? Right. So no, that's a pretty normal thing. Pretty legit. All right. I'm gonna do this one, but we're gonna take like a 5-minute break because I want you to clear it. Clear your head somehow, whatever that, however you do that, clear your head. I walk outside, so that's what I'm gonna do. All right, so this one says, again, find the reactions. So this is all still chapter 4. After this one, we'll go back and we'll think about chapter 1, 2, and 3. So that'll get you all prepped up for Wednesday. So this one says, it actually says find the wall reactions, but same thing, right? So that means we take away the supports, we put in the reactions. So how many for a pin at A? 2. So an X and a Y, which way do you think the Y goes? Up or down? Up, I agree. A, Y. And then what do you think about the X? Left or right? To the left? Yeah, probably to the left, although we do have the 200 going to the right. So there is, don't you see that? 200? Oh, sorry, going to the left, right? So if we needed to oppose that, which way would we put it? To the right. But this one also has right effect. This one has right effect. So there's left effect and there's right effect out here. So honestly, I don't know which way it goes. I don't know which one's bigger. What? I agree. Yeah. Yep, I agree. Like if you think about, oh, what about these? What are these doing? They're trying to pull it down, right? This way. So this probably goes that way. So we'll make a good educated guess here on AX. But again, sometimes you don't know. Like if this was 10,000, I'd be like, I don't know which way that goes then for sure. It might have to actually push to the right. So again, it's just a guess. What do you think about B? We get 1 for a roller, right? And it's always perpendicular to the surface removed. So the surface removed was vertical. So perpendicular to the surface removed is horizontal. So it, with all this kind of trying to lever it down, this is probably trying to push it to the right. But again, it's a guess. It's all it is a guess. Perfect. Thank you. I'm thinking ahead. I'm thinking probably too far ahead. So, all right. So now I think the best strategy is get your free body diagram done, right? So put the 600 in. We already have our reactions in. Put the 800 in. Right? Put the 200 in. Those are all the X and Y forces. And then for the angled forces, put in their components. Don't put in their angled forces because that's going to be a tough moment, right? Figuring out that perpendicular distance and all those crazy things. So break the 400 into its components here and here and find those, and the 500 in to its components and find those. Okay. So if I'm going to use the 50 degrees on that 400, and if I want this opposite side, that sine, so it should be sine 50 times 400 for this down force. 306,417. Everyone see what I'm doing? 41778. Right? I'm just finding the components of the 400-pound force and putting it in the free body diagram. So then the next one is cosine 50 times 400. 257.115. The glare is just terrible in my calculator. 257.115. Just for space, I'm gonna cut those a little short. Same thing over here. So this one's gonna be 50 sine 500 for the Y, 383.022. And I know that these point down because this has down effect. And I know they point to the right because it has to the right effect. So then 50 cosine, 500 times, and 321,394. All right. So then you have that. It ends up free body diagram. It should stand alone, all by itself. No need to look back at the previous problem. I have the distance 6, I have 8, 8, and 8. I have all these X and Y forces at their location. It did not label all the points, but I did. Notice I left out the internal structure because I don't care about that. We don't look at that internal structure until we take it apart. And that's chapter 5. Right now, we're just dealing with the external forces to this system, right? And we want these reactions. That's our goal. So I don't really care what's inside or what it's made out of in there or anything like that, because I'm not taking this thing apart. I'm leaving it together as one solid system. Okay? So now what do we do? How do we find these? Yeah, same way we have always found them. Regardless of how complicated it looks, we are going to sum forces in the X, and we are going to sum forces in the Y, and we are going to sum a moment somewhere. That's how we're going to go after it. So at this point, you can say, like, which one do you want to do first? Doesn't really matter, but is there one you want to do? Is there one where you can solve for something? Because you don't have to do them in this order. You can do them in any order you want. How many unknowns are in the Y? 1. You can solve for AY right now, right? How many unknowns in the X? 2. Probably don't want to do that one right now. Like, that's, I can do it later, but, and I might need it at some point, but I'm not going to do it. And then we could sum a moment somewhere, couldn't we? Where? If we did point B, what drops out? If we did a moment at point B, what would drop out? Which force does not contribute to a moment at point B? AY does not contribute because it goes right through the point. That's correct. What other force? Yeah, BX, the easy one. Does not contribute to the moment here at B. G is just, G's a point. We're talking forces. Any other forces that do not contribute to the moment at point B? No, the rest of them do. Yeah. All right. What if we did a moment at A? What does not contribute to the moment at A? Yeah, get the easy ones. AY and AX do not contribute. What else? No other forces go straight through point A? Really? That X force goes right through that point, does not create a moment. That X force does not create a moment, goes right through that point. What about the 200? Does not create moment, goes right through the point. So the forces that drop out of the moment equation at point A, 1, 2, 3, 4, 5 of them. I'm liking that. I'm gonna have to do any of those, right? So this is a great spot to do a moment. All right. Let's do, you identified this first, so let's do this. Some forces and Y. What are all the forces in the Y direction? No, when you're doing forces, you're not doing it at a point, right? It's just forces. The only time you need a point is moments. So when you're doing forces in the X, you don't need a point. You're just doing all the forces in the X. And you're doing forces in the Y, you just look for all the forces in the Y and write them down. So AY up. No, when it's not a moment. Don't do moments. It's easy to mix it. Plus? Yeah, minus. Y minus? Nope. We're not doing moments. Y minus 383. Correct. When we're doing forces, it's just whether they point down or up for the Y. And when we're doing forces here, it's whether they point to the right or to the left. That's it. That's how you get the sign. This is rotation. This is whether it's going this way or this way. This is whether it's going up or down. This is whether it's going right or left. That's the signs. All right, good. What else? Well, what are they? Geez, I'd like to work around some logical method. How about that, Ben? Thanks, man. Just for me, I'm old. So we got that one, that one, that one. Thank you. Thank you. What else? That's it. That one, that one, that one, that one, that one. Good. And do what? Set it equal to 0. Excellent. How many unknowns? Boom, we have one of our answers right there. Because we chose that equation because there was only one unknown. Right? All these down effects, down, 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 has to be balanced with that up effect. That makes sense? Excellent. So then you just like flip and add them all up, right? It's a big number. We have 6.4, 1.778, and 383. I think I got it. Yeah, 2089. $2089.45. That's what I get. Pounds. So there's a whole bunch of, that's called shear. There's a whole bunch of shear going on at this pin. Like this whole truss just wants to go straight down. The only thing stopping it from going straight down is that pin right up here. So if I was going to design this pin, I need to know that there's 2K acting on that pin in shear, just trying to shear it off. So if I build that pin out of 1-inch wood dowel, it's gone. It's just going to disappear, right? Even 1-inch mild steel, I'm going to want to run that shear stress equation to figure that out, right? But I'm probably getting closer to something that'll hold, or maybe 8 half-inch bolts. You know, whatever we decide there, it's got to carry that load. That's the point. That's why we do this. That is the only reason we do this. Pain. All right. So what else now? I need X, I need BX and AX, these two things. So they're both in the X. You can run this equation, but you're going to end up with two unknown. So I'm not going to waste my time with that. So forget that. I'm going to do a moment. We already talked about moments. And we know if we do a moment here, there's a whole bunch of stuff that drops out, right? So I'm doing my moment at A. So now we just have to methodically work our way through it. And I would work around the system so I don't miss anything. You've already identified that these two drop out of the moment at A, and that one drops out, and that one drops out, and that one drops out. So I'm not even going to think about those. They go right through the point. I am doing moments now. The 383, does it create moment about this location? Absolutely. That moment is just like that. It's going to rotate around point A. So I'm going to include that. What's the distance? Yep. And what's the rotation? Yep. Just do them one at a time. Don't look at the whole picture. That one is done. What about this one? Does it create moment? Yep. What's its distance? 16. And rotating that way, negative. What about the 800? Does its line of action have a perpendicular distance to point A? Absolutely. What is that distance? 24. And if I kind of slid it up here and put it there, how's it rotating about point A? Yeah, same way. What about the 600? Same kind of thing, line of action. Kind of slide it up here, 8 feet, right? And its rotation also clockwise. Whoa, we got that one. You fell asleep there for a second, Ben, but you woke back up, man. You're here now. So we worked our way all the way around. What about BX? Does it create moment about point A? Yeah, absolutely. That's the one we want. BX times what? 0. It goes right through point A. Yeah, it doesn't go through point A. It's like down here, and that's the perpendicular distance, 6. And then which way does it rotate? Okay, something better rotate positive, because we have negative, 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 negative. Something's got to rotate positive for this thing to be in balance. And it's BX fighting everything, fighting that, all of those rotations. Poor little roller down there is fighting it. Set it equal to 0. Solve for BX. We'll leave it there because it's positive, and we'll move all these negatives to the other side. And they all become positive, giving us a positive value for BX. All right, I'm going to crunch it. Somebody else crunch it too. That's rude. I don't think they can see. I think that's invisible unless you're like in person type of thing. Oh, I can minimize it. There you go. I am trying to be smarter than the technology, but that doesn't always happen. That calculator is supposed to come out at the beginning of class. And you're supposed to calculate everything that I calculate to keep me honest, because I am capable of making mistakes. Whew, I get a big number for BX. I just wrote it in pen too, so I really committed. I screwed up the second time. Got the same number twice in a row. Anyone else get that? 5327? All right, we're gonna assume that's correct. Nobody's verifying that with me yet, but we got to keep going. We're on a time frame here. So once I have BX and it comes out positive, that's important because that means I assumed the correct direction in BX. BX does point into the structure. The wall was holding it away. That makes sense. All right. How do I get AX? So that's the one I don't know. I know AY, I calculated that. I know BX, I calculated that. So that one's done. That one's done, but that one is not. How do we get AX? We know BX. Now we only have one unknown in the X. So we could do X equation, right? We could also do another moment. You could do a moment down here if you really like this complicated force times distance stuff over and over and over. You could do another moment. That would work. But you could also just run the X equation. So some forces in the X. What are all the forces in the X? We got this one, 321, 394. Minus the 200. And we got the BX, 5327. 5327.81. What else? So we got that one, that one, that one, and this one. Yeah, minus AX. We put it in going negative. So you got to put it in going negative. Should have only one unknown when you do that. But you need the unknown or you got nothing to solve. So since it's negative, I would move it to the other side and then all these signs stay the same. So we got the positive 5327. We've got a 200 that's negative. We've got a 257. So I get AX at 5706.32. Excellent. So now I'm just writing them in. Reactions are done. Right, AY 2089, 5706 for the X at A, and 5327 for this roller at B. If I wanted the full load on A, it's the combination of these two. So the full load on A is big, big. Square that, pathetic green theorem it, and you'll get the full load. But we don't need that till next term. So next term, that's the first 1/3 of the problem right there. And the next 2/3 is all strength of materials. Bending stress, tensile stress, torsional stress, shear stress, deflection. Good times. None of it's calculus based. So if you wrap that around calculus based, then you're going deep. All right. Good. Does that help? Hopefully that helps. Will you see one like this on the midterm? Probably not that complicated. Like I actually might give you a truss, but then I'll probably give you like 2 loads on it, right? And say, hey, find the reactions. Or I'll say, find the resultant. So that's the difference. We need to make sure that we understand the difference. So I could give you this. I'm just making this up. Some kind of wacky truss just to stress you out, right? And a roller and a pin and a wall and a load like this of 4 kips and a load like this of 2 kips, and then 10 feet, 10 feet, and 7 feet. A and B. Oh, sorry. There. Now you can absorb it. Right? So, chapter 4 is what we just did. And that would be find reactions. That's just what we did, right? Free body diagram. These are the reactions. Find them. Chapter 3 is find resultant. What was that? Anybody remember what that was? What forces? That's exactly right, but let's clarify. Adding the external forces, anything out there, right? So external forces, we leave the supports there. We just ignored them for 3 chapters, chapter 1, chapter 2, and chapter 3. We ignored whatever those were. We didn't even know what they were, right? So the resultant says, take the 2K and the 4K and turn it into one force. Okay. And I would probably ask you like, and then tell me where it is along the top of the structure or along the bottom of the structure, something like that. Yeah. So how did we do that? How did we like combine these things? No. What did we do first? This is why we're doing this, to remember. Didn't we like move? We want to move all the forces to one spot, right? That's what we did, is we moved everything to one spot. How can we do that? Like if I said, okay, I'm going to move them all to point A. I gotta move them somewhere, right? You gotta move them somewhere, and how do I do that? So the way I did it was I was just like, oh, well, if it's along that line of action, can't I just take the 2K and move it over there? I can, yes, that's called the principle of transmissibility. I can move a force along its line of action anywhere I want to, because there's no moment involved. We know that now. The 2K, if I moved it to here, doesn't change the effect because that goes right through that spot. There's no additional moment. I just move the 2K to there. Or there, if I choose A. So if I'm going to move it to A, the 2K, I just move it. Now it's gone. I can do that. It's called the principle of transmissibility. It's the same as I push on a car or I pull on a car, same effect. What about the 4K? Can I just move it to there and not do anything else? No, because its line of action does not go straight through A, right? The translational effect, the 4K, yeah, I can just move it right over there. 4K, but what's got to go with it? The rotation, the moment's got to go with it, because doesn't 4K create moment about this point, the point I chose to collect them? Yeah, what's the moment? Oh, I know moment is force times distance. 4K times 20. Yep. Wait, whoa, 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 whoa. Don't be jumping around mentally with me here. What we just did this for the 4K, right? So that comes over here. 80 kip feet, correct? Now that's gone. So I move everything to one spot. Now, what do you want to do with the 7? Nothing, right? That's just a distance. Yeah, exactly. All right. You just got to slow it down, Ben. I think you just got to slow it down. All right. So now everything's moved here. How do I find the resultant? Remember, the resultant is just a force, a single force. You got 2K to the left, 4K down. How do I turn that into one force? He said it earlier. So this is what we have. Oh, this is what we have, right? How do I turn that into a resultant? Yeah, add them together, tip to tail, 2K, and then what's that thing called right there? The resultant, correct. You know, two sides. Pythagorean theorem gives you 16 plus 4 is 20. I should not do it in my head. 4 squared, 2 squared, add them together, square root them. 4.472. That's the resultant. All right. Now, it's not all we need. What else do we need? That's just the magnitude. Where is it? Right. Where is it? So how do we know where it is? Let's say on this upper chord, it's called a chord, this upper area of the truss. How do I know? I know it's kind of like down and to the left. So I know it's either out here down to the left or out here down to the left. How do I know which way it is, where it is? Right? I know it's out here somewhere or it's out here somewhere. Yep. Our moment tells us where it is. We have to make this moment. So if I put it over here, Would that force create that kind of a rotation about that point? Yep. If I put it over here, it's going to make that kind of rotation. That's not the same as this. So this is not correct. It's not out there. And how do I know where it goes? Yep. We take the moment and we divide by the Y force. If we divide by the 4K, we get a X distance. If we divide by the 2K, we get a Y distance, and we want an X distance. So we take the 80 kip feet and divide by the Y component of 4K. That tells us where it's at. Where is it? 80 divided by 4? 20? It's right here. And we would also want that angle theta. Yeah, so when you have an angled force like this, and that's all right here, correct? And so where I wanted, and this would have been in the problem statement, I would have said, hey, find the resultant at the top of the truss, right? So that means I want the resultant along this line. So if the resultant is going to land along this line, the 2K does not contribute to the moment. So when you say, oh, the 80 kip feet, it's all made from the 4K, none from the 2K. I don't know if that makes sense or not, but when we did the 4K, right, we multiplied by this distance, and that's what's created the moment. The 2K was here. It didn't make any moment. So all of this moment is made by the 4K. So that's why we divide by the 4K. And that brings us back to a nice, clean, horizontal distance because we used a vertical component. Yeah. Yeah. So anyone find it interesting? The resultant comes right back to this point. Yeah. Anyone know kind of why, how that happens? So yeah, remember the 4K was here and the 2K was here, correct? And I had you move everything here because I wanted you to go through that process. Like, oh, I remember now how we moved stuff. That was good. But couldn't I have just moved the 4K up to here and had 2K and 4K at the same spot? Yeah, way easier because now when you find the resultant, it's right there, R, which is what you found anyway by moving it. Like you can move the forces anywhere and it will give you the correct answer when you move it back out. But there are easier and harder ways to do it. This would have been much faster just to move the 4K up to here. No moment, because they both go through that spot, right? Pythagorean theorem out, the resultant, you got it, you're done. So you wouldn't have done any of that fancy stuff. But you also wouldn't have remembered the process. So that's going to take some reviewing. We haven't done that in a while. So the find the reaction thing, that's more current. So maybe, practice this a little on simpler problems. Remember what to do with distributions. And you're ready for chapter 4. Go back, look at this for chapter 3. That's going to be important. And then chapter 2 and 1. And I'll give you one of these. And it should be just a bonus if you read the problem carefully, but I might give you something like this. And this is emphasizing chapter 2. Right about now, you should be going, what the heck? This looks hard, right? And then, I don't know, put a ruler and a pin, give you a whole problem, right? And all the distances. 2, 2, 1, 2. But then the problem says, find the rectangular components of the 47 kip force. Okay, that's it. That's all you have to do. So what's that mean? Find the components of the 47 kip force. Yeah, that's X and Y. That's this and this. Find this F Y. Find this F X. Done. Move on. Next problem. That's a bone. I'm just throwing you a bone, like, do it. Swear every year a student will like put in the reactions, solve the whole damn thing. Like, no, this is not what I asked, right? Just find the components of a force. That's chapter 2. All right. So just read the problem really careful and only do what you need to. And again, if you're here, ask if you're not sure. Like, somebody will always ask me, like, is this really all you want me to do? I'm like, yeah, just do what it asks. Yep. Right. Just don't complicate things until you need to. So yeah, separate that stuff out and I think you'll be set. So spend a little time, open book, open notes, organize your thoughts. Like, hey, if it's a non-concurrent problem like this, what do I got to do? If it's a concurrent problem, what do I got to do? Yeah. Yeah, absolutely. Yep. I trust you guys. Yep. Questions? It's always a good time. Wednesday will be fun. It'll be boring for me. All right, we're good. We're done. If you're going through anything, like if you're studying and you have questions, don't hesitate to reach out.